So welcome back. We're going to continue on in lesson 5 and continue our way through failure mechanisms. And in this portion of the lesson, we're going to really talk about fatigue, which is one of those really important considerations in failure that we should look at, but it's something that we don't always pay as much attention to as we should. So we're going to go through explaining what fatigue is and really identify a couple problems. And before we get there, I'll show you a couple of the reasons why fatigue is really something critical. So as we do with most of these lectures, we'll start off with a little quote. This one from Arthur C. Clarke. So if you've seen 2001 Space Odyssey, it was his book initially. He's a science fiction writer. And so I tend to like this one is that, when somebody, in this case, he goes like an elderly scientist, but you can look at it as more professional, because I'm not sure whether you look at me as elderly or not. I'm not quite at that level. But they tell you when something is possible is always right. When something's impossible, probably very wrong. And so sometimes what he's getting at is we get set in our ways. And I think fatigue is one of those things because it sneaks up on us. And I saw really a connection between this type of quote and what we're going to be talking about today. So when we talk about fatigue, it's not so much the tiring or you're fatigued listening to me in these lectures as they go on too long. But really what fatigue is, especially in design and in materials and in mechanical properties as we study them, is really the idea of cyclic loading, where we load something up and we unload it. So it's very much like real life. And we saw that example going back to the initial lecture that I gave and showed you the Aloha Airlines flight, where really the fatigue in that case was the loading and unloading on the fuselage of pressurizing and depressurizing the cabin as they would go up to altitude and back down. So the SN curve, when we have it as far as our second one, is really the way of looking at fatigue as far as the engineering stress strain curve that we looked at for general mechanical properties. So what we're going to see is when we look even at our next section in creep is there are different ways of looking at these failure mechanisms and how they're loaded and unloaded. In this case, the S refers to stress, as you would imagine. N is number of cycles to failure. So these are two things that we look at. And one thing to bring out of the fatigue curve, and something that is a bit pet peeve of mine when I'm talking to other engineers or talking about people with design or in some of my previous positions is when fatigue came up, people will typically say it has a fatigue strength of X. But in fatigue, that doesn't really tell you anything because you know the stress, but you also have to know the cycles to failure. They both define fatigue. So you'll hear when I talk about fatigue, and we'll keep harping on this. The other idea is the idea of a crack initiation and propagation. And those are two very distinct things. We talked about it in sort of the fracture and the fracture mechanics ideas of it, but these tend to really take on a bit more significance when it comes to fatigue, because fatigue and sort of failures due to the cyclic loading become very susceptible to initiation, because initiation takes a while to occur, but once initiation passes and you get to propagation, things happen quickly. So what we're going to see is fatigue is really sort of this unexpected failure that happens catastrophically. And so whenever you use the word catastrophically when you're talking about failure, things are happening rapidly when you don't expect them. These are when disasters occur. And so we'll see how these disasters go. And we'll talk about factors that affect fatigue life. I guess the way I look at it is things that show up in the toolkit of whether it's a materials engineer or a structural engineer or a design engineer. When you're designing something, what can I do to try to extend fatigue life or mitigate fatigue? And then the environmental effects that come into that, because there are things like corrosion fatigue that we're going to see that are out there that are growing in consideration and study, because as parts get older and our components are lasting longer, we're exposing them to different environments. And as we see as climate change comes around, is some of these existing environments that we're putting materials in, they're going to differ. And so things that we need to take into account. So just on the baseline of that. So we have our book that we're going to go to. So go to chapter 8 in Callister if you don't understand anything, and always to the Canvas pages. So what we see here, though, is a different when we go to the terminology. There's some different ones that we haven't seen before. So fatigue, of course, is at the top, but we see high cycle and low cycle fatigue at the bottom. And that refers to the number of cycles where fatigue occurs and where the stress amplitude, and we'll explain a lot of that. Fatigue limit is something. As mechanical engineers, sometimes it's referred to as the endurance limit. We're going to see that certain materials have very unique characteristics. where they do not fail by fatigue below a certain stress level, and that's what the fatigue limit is. And so fatigue life and fatigue strength, those two components of describing fatigue properties, SN curve, but what we see is how we test them is really stress amplitude and stress ratio are going to become. So if you put a little star by stress ratio, and if you're going to write anything, R, capital R is what is called by stress ratio. And it's a term that's thrown around a lot when people are talking about fatigue, and there's always the assumption that everybody knows what they're talking about when they use that term. So we're going to explain it and give you a little bit of a head start when you're going through it. So what is fatigue? It's failure mode, and it occurs when different structures or components are subjected to these dynamic and fluctuating stresses. And so typically what we're looking at is these stress levels that we're continually exposing and taking and applying them to and coming down really are below that yield strength. We can say here it's considerably lower than the tensile yield strength, but we're going to concentrate primarily on yield. So it's in the elastic section of the curve. Now, you start thinking about that, they shouldn't fail. They should never fail, correct? Because it's well below that ultimate tensile strength, the strain levels that we're talking about. But what we're going to see is the failure occurs. The little scary thing about it is that about 90% of all metallic failures, an estimate, so they fail by other ways, but fatigue is up there. 90% of all failures occur by fatigue. So you would assume with something that occurs so commonly that we would study it in more detail. But we typically don't. What we tend to see too, another thing to bring about is that the failure modes are brittle. So when you look at the fracture surfaces are going to look different than that dimpled surface that we talked about with ductile failure mechanisms. Really, no plastic deformation, little to no warning. And so that's where the catastrophic failures come in, where something fails without warning catastrophically. And we're going to see what can happen with that. So a couple examples. So I'm going to show one video here, and this was an animation. This was F-15C at the time. It was in 2007. This was a training flight over Utah, and so this is an animation of what happened. And so what you're going to basically see is that this aircraft, which was a fighter interceptor, it's an F-15, so it's a fast. This basically Air Force pilot. He's a fighter pilot. He's going through flying around doing what fighter pilots typically do, wants to go fast. He's sort of the Ricky Bobby of the pilots when you go to it. And what we're going to see here is he had a little bit of a surprise. The aircraft literally broke into two pieces, and it was due to a fatigue failure. So I'll let you watch the video, and you can imagine his surprise when it happened as well. So this pilot was on a training flight. He survived this, so in real life. But there were two incidents where these things happened, and the U.S. was forced at that time to ground the entire fleet of F-15s to try to figure out what it was. So we'll let you watch the video first, and we'll go into what actually happened. So as you can imagine, he was a little surprised by that, and a lot of people were. And this was a really pretty big deal when it did happen. And so they started really going about. So they were able to grab what was left of the aircraft on the ground and start looking around to what was going on. And as they started looking through other F-15s, they started finding a concerning crack developing. And so the longerons are these structural components, and you can imagine why they call them longerons. They're along the length of the aircraft. And so they're longitudinal members, and they basically are supposed to transfer skin loads to the internal structure. But they started seeing fatigue failures in them. So they had to go through and replace all of these structural components because these cracks started occurring. Now, why did the cracks occur? Well, the F-15Cs were mostly built in the 1970s, so this was about 2007 when these failures started to occur. We also were in the midst of the global war on terror, so these aircraft were flying much more than they would have in a typical peacetime training regime. So old aircraft that were made older by significant increases in duty cycles, fatigue failures are a big problem. So they're constantly, the Air Force flight crews, commercial aircraft, they're constantly looking for these types of things so they can avoid these types of failures or these accidents. Now, another one that I'll bring up is fatigue led to the deadliest air disaster in American history. So in 1979 at O'Hare, DC-10 actually crashed. So this was the last photograph of it. But what had happened was the left engine, so you can see the smoke coming there, the left engine literally came off the aircraft on takeoff. And it sliced through the hydraulics on the back of the aircraft, ripped through this 3-foot section of the leading edge. So they lost the leading edge of the wing. The hydraulics were all gone. The pilots had no. So 258 passengers and 13 crew members. So basically at O'Hare International Airport, if you've ever been there, it crashed off the end of the runway into basically into a warehouse. Now, what led to that? So it's a little different than just old life. This was a fairly new aircraft, 1979 DC-10s. And if you follow aviation history a little bit, DC-10s have never had a really good history, especially at that time. There was a problem with a cargo door. So they had cargo doors that were coming off in flight. And there was a major accident at Paris de Gaulle International Airport where an aircraft crashed on landing because the cargo door came and went through basically the tail section of the airplane. And there were a couple other accidents. So this aircraft in and of itself had a bad history. But part of what led to this one, and as they started looking at it, this isn't a case like we saw with the F-15 where it's just the aircraft got old and so the fatigue cycles built up. This was a case where they actually induced conditions that would lead to fatigue failures. And as you can start to see is they reused what was considered an unauthorized maintenance procedure. So in order to basically work on the engine, they had to remove the entire engine housing from the wing. And they're required to, from maintenance schedules, to pull these engines off and look at this. So basically the DC-10 was a Douglas aircraft, so it's a McDonnell Douglas aircraft part. The McDonnell Douglas requirements for it required them to almost manually take this off. They had to have lifts. It was an incredibly long procedure, and so American Airlines basically found a way to try to save 200 man hours. That's a lot. So time is money. These types of man hours and these labor costs are one of the big cost drivers for the aviation industry and the commercial aviation industry. So they found a way to try to save it. So what they did was they used a forklift to lift the engine up and to place it back in. Now, if you think about it, United had the same problems. They had the same aircraft in service. They used overhead cranes to lift it up. So you had a lot more control with the overhead cranes. The forklift lifted it up, and basically on the pylon, they basically were pushing the engine into it, and the forklift kept running into the pylon until they could get it straight. So what they did was they started inducing surface damage on the pylon. What we're going to see is surface damage is one of the leading initiators of fatigue failures. And so what this was basically a maintenance procedure, and so not really thinking of how you were doing that maintenance procedure led to an eventual fatigue failure. And so the fatigue crack developed and it expanded over an 8-week period after they had taken it out of maintenance. So it goes back very similar to that Kansas City Hyatt Regency disaster that we had talked about before, where not quite understanding what you do during manufacturing or during maintenance can impact design requirements. So we'll step away from those, and so now we sort of, I think I've got your attention at this point on how critical fatigue is and how we really need to consider it. So how does stress vary with time? And so there's a couple different ways to do it, and what I want you to think about when we start looking at these is, okay, it's going to probably in practice be a little more random than we tend to think, but how do we standardize a process for looking at fatigue? And that's sort of where we can reverse stress cycles, where we go from tension to compression, or we can repeat the stress cycle where we take it up to, in this case, in tension at a maximum level, bring it down to slightly in compression or not in compression. We can take it down to a little above zero and then back up where we're repeating the stress cycle, or we can just have these random cycles. The random cycles, as far as a testing procedure, if we can't do it the same way each and every time, and what we're going to see is scatter and fatigue data is another real problem that we have, is that you can't really test it. There's no baseline for getting a good measurement of what the fatigue properties of the material are. So we can test them, either tension compression, and this is probably one of the more common ones. We can bend or we can twist, this torsional loading. And what we're going to see is tension compression and twisting are the two most common standard test procedures. So rotating bending fatigue is another term to use along with the axial fatigue levels. And so, to be honest, in a lot of cases, I hadn't really looked at fatigue a lot earlier in my career. Over the last several years, fatigue has become a big part of what some of my research is working in. And part of that is driven by the work we're doing in additive manufacturing and trying to develop standards for use of additively manufactured parts in fatigue conditions. So we're thinking, in my research group, we're actually thinking about a little bit of these types of things. And so what we tend to see in the reverse stress cycle is this regular sinusoidal dependence. Looks like a sine wave. And so the amplitude is really symmetrical, and it alternates between a maximum stress to a minimum compressive stress. So we're taking it in compression and basically taking a bar, think about it, pulling it, squeezing it, pulling it and pushing it up and down. Repeated stress cycles are a little typical to what we look at. And so what we end up can define a couple different things. So we have our stress amplitudes and our minimum stress. So we can define a mean stress out of that, or just the average of it, just as it says the range of stress. But the stress amplitude is mostly what people will define. And it's basically that max minus the min over 2. Very similar to what we had with the mean stress that we had looked at. Now the important one to come out of this is the stress ratio, is the ratio of that min to the max. So what you're going to see is people will talk about doing fatigue testing, and they'll say, I have an R value of 0.1. And that tells you, for the most part, in this case, we're considering tension to be the plus, the positive, compression to be the negative. So if you don't have a negative value there, so if it's just 0.1, it tells you that it's always in tension. So 0.1 over 1 tells you that you have a maximum. So this min would be at 0.1 of your maximum as you look at it. So you can normalize these and think about it. So if it's R equals -1, your max and your min stresses are equivalent, but one is negative. And so you should have fully loading and unloading. So when we think about a reverse stress cycle, that's an R value of -1. So random stress, you really can't define this. It's not something. This is more something that you would put into service or look at service conditions and try to track if you have, for the most part, the analytics or the telemetry or sensors on it to tell you what the stress levels are, and you're looking for peaks and valleys of the stress that you're seeing. Now in fatigue testing, what I sort of showed here is I just grabbed one. So an axial tension test is very similar. So the machines, you would look at the sample geometry. It would be a little different because we worry in fatigue a little more about what we call these sort of fillets here. They're not fillets, they're called fillets. So I've had students treat me. A fillet is something I like to have with dinner. A fillet is what I have when I'm looking at these types of things or at weld joints. But what I can do is, what I see here is the rotating bending fatigue. And so basically I might put a weight on one of these or some type of load, and I'm just rotating this. And in some cases what I'll do is I'll drop seawater on it if I want to look at corrosion fatigue or the role of corrosion on that. But these types of the rate angle or the radius of curvature of these fillets, we go back to maximum stress levels. These are really important. And it's almost a point of contention within this testing is people cannot agree on what this fillet can be or should be. So what you tend to see is there's a lot of rotating bending fatigue, usually done in terms of corrosion. Most of it is done at axial fatigue, and those systems are going to look exactly like what you would see in a basic mechanical test or a tensile test, as we might look at it. But what we see here is we see a lot of control going on here, and we see standards that tell us how to do these types of tests. And we always go back to these ASTM standards in order for sample geometry and for testing modes. So a couple other ways, and so what I wanted to show here was sort of what you typically get in practice. So outside of the tests that run fatigue tests, bicycles are one area that we can go back to and say, yes, they see a lot of fatigue, especially when we talk about the frames and as you're pedaling and as you're hitting bumps in the road, especially here. We know this very well in Pennsylvania, that our roads aren't always in the best shape. And so you're either running over cracks or you hit a pothole or something. And so these are a couple different tests that you can sort of look at. They don't tell you a whole lot about the actual fatigue life, but this is sort of what we consider sort of an in-service type test for looking at fatigue. So if you're the engineer running those tests, not a very exciting test. So day in, day out probably of just running through loads and watching them and trying to figure out at what point they fail. So they have mechanical counters there to tell you the cycles. But they don't tell us how to construct SN curves. So SN curves really come out of this idea of being able to have our engineering stress strain curves for fatigue conditions. And so they're going to look a little differently. So on the y-axis, we have that stress amplitude that we calculated earlier when we talked about the stress levels, and the cycles to failure. And usually that is a logarithmic scale, because we tend to see that when we talk about cycles to failure, we have these different numbers, and so they're typically pretty high levels. So 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th. So we're talking about millions of cycles that we test these on at this given stress amplitude. And so we want to subject this specimen to the stress cycling. And one way to start, and usually a starting point, is you get about to 2/3 of the static tensile strength. So as I said, is we can talk about tensile strength, but usually I would probably substitute in most cases that for the yield strength. And that's going to just basically, you test it at that stress amplitude level, you get your number of cycles to failure. You keep your R value consistent. What you can start doing is just repeating these over and over again. And so the fatigue strength is the stress level at which failure will occur, and the number of cycles to failure is the number of cycles to failure at that given stress level. So as I said, these are the two things you need to report. So if you have fatigue data, both of them needed to be reported. Now, one thing that I would probably say is usually on these types of plots, we have this nice line, and so everybody tends to think that fatigue is this nice clean area. I would say is if you're really going to be honest with yourself as far as what this line should be, it should be like 10 to 20 point line. It should be a really wide line, because that shape may be there, but there's always a lot of inherent scatter. And so for a lot of materials people, one of the things that we don't always like to work with is math. And when we go to math, if we take that down to a different subset of math, statistics are never a real popular subject either. And so when you start talking about the statistics of the scatter from this SN curve and how you would determine this line and how you determine safety factors and going through and identifying uncertainty and variability and all of these things that statisticians tend to do, fatigue is really where a lot of that gets put to its test. And so there's a lot of use of these terms in there. So having that inherent scatter in your mind as we start working through this is important. So how do we construct an SN curve? So we see here as we have a nice SN curve, we start with a certain number of tests. And so all these SN curves, they're not calculated per se. They are based on actual experimental data. So we can start with different stress amplitudes, and as good experimental practice, you do probably at least 3 tests at each of these stress amplitudes. So you would end up with error bars or get an idea what that scatter would be at each of these. And you for the most part, count cycles to failure. So what is the fatigue strength at 4 times 10 to the 6 cycles? For A, we go to 4 times 10 to the 6, go up. What we're going to find here is that fatigue strength is going to be a little lower than what we see there. So about 120 megapascals at 4 times 10 to the 6th. And so it gives us that. So the fatigue life at 120 megapascals is there. So what we see is that for a fatigue strength at 4 times 10 to the 6th is about 100 megapascals. We see that the cycles to failure actually sort of went down to a point. So it's actually at a lower level. So as we go to 120, we're going to a higher stress amplitude. Our cycles to failures goes down, and we see that in the curve. So they take on this type of declining shape with amplitude. So high stress amplitudes, low cycles to failure. What we're going to see is that's low cycle fatigue. High cycle fatigue is low stress amplitudes, high cycles to failure. So some materials, though, provide us with something that's really interesting. And what they do is, rather than continuing down into sort of this infinity and into almost into a zero or coming down here, they will reach a point where after a certain stress level, and it goes no lower, they don't fail by fatigue. And what we typically will call these in testing is their run out. So we'll test something to say 10 to the 7th, 10 to the 8th cycles to failure. We'll say it's a run out. It didn't fail at that point. And so this is how we start to define sort of fatigue limits for a certain number of stress amplitudes or a certain number of cycles to failure. So we can limit the stress level. So if a material displays a fatigue limit, or an endurance limit is another way to put it, and typically ferrous-based materials, titanium alloys as well, and they typically are between about 35 and 60% of the tensile strength. We just basically make parts big enough that we get the stress levels down below this fatigue limit, and so then we can sort of make ourselves feel a little better that we don't have to worry about fatigue. So fatigue becomes not an issue. Now what we notice here is non-ferrous alloys tend to display no fatigue limit. Things like aluminum. Where do we use aluminum a lot? Aircraft. So when we start thinking in terms of how aircraft are going to operate, aircraft are susceptible to fatigue failures because of the material choices we made.